H bridge, coil, right? And then I'm only going to draw part of it. And then somewhere over here, you've got power supply, right? So that's half of it. So when you apply current to this coil right there, and you make current flow, what does the motor do? That's the motor, right? What's the motor do? So let's answer this. It turns. That's 2. What else could happen? These are multiple choices on a test. How about nothing? How about I don't know, it heats up. Or it jumps to a position. What do you think? 1, 2, 3, or 4? Let's deal with number 1. Okay, let's deal with number 1. It turns. No, it doesn't turn. However, if it was a DC motor, a single phase motor, and you applied current to it, and it was a DC motor, it would turn. Since it's a stepper motor, and a stepper motor, in order to make it turn, you have to go through that 4-step sequence. And when you look to your Arduino libraries, one of the things that when it said, yes, here's a library to run a stepper motor with an Arduino. What did it do? It said, oh, you must use these 4 outputs, and you have to sequence these 4 outputs in a certain fashion. And when you go that one, when you turn on output 1, it goes click. Now you better turn on output 3 next, and it'll go click to the next spot. And then you go back to 2. You know, there's a specific state sequence that it goes through because you have to get it to click to the next energized. You know, it's basically a magnet following energized electromagnets. And in the stepper motor, let me draw. And so here is your stepper motor. That's the outside of it. Right, and inside of that is the rotor, and on the rotor is a bunch of magnets. Now this is simplified and incorrect drawing of it, but I'm just kind of showing you. So you would have north, south, north, south, north, south. You'd have a bunch of magnets, but the point is there's magnets on the rotor of the motor. Around the outside is your coils, and they're repeated, and there's some that are phase A and some that are phase B, but there's a bunch of coils, and that they are all static and fixed in place, so they don't move. So what do you get to energize? You get to energize, let's say you energize that one. Okay, that's the first state in the state table from your Arduino. That turned on output 1 from your Arduino, and you energize that one because that turned on that transistor and that transistor. And that happened to be that coil. What did the rotor do? These north-south magnets lined up, and it aligned itself such that if this was north and south, then south and north, this one would have wanted to align kind of like that, and it probably would have shifted slightly that way to get that into alignment along that. Make sense? So you turned on this coil, and the rotor was slightly over here, and it needed to move this way until that south and north aligned with that south and north, and then it was perfectly aligned, and it stopped. And it had holding torque. As long as you left the current on, it just sat there. Okay, so number one is so this is why good thing I'm not writing a test, because number one is it did just turn, didn't it? But it didn't keep turning. It turned to a position. So it turns, if I wrote it turns constantly, that would be wrong. It doesn't turn constantly. Okay, nothing. Could nothing be the answer? Well, no, nothing can't be the answer there, because this is one of the things you'll need to do is, here's the shaft of the motor. If you actually physically grab the shaft of the motor and twist it, I wouldn't spin it. You never, never, never spin, because if it's a servo, you're creating error and you build up error. It's always grab the motor shaft and turn it a little bit. So everybody got your motor? Does anybody have your motors handy? If you got one of your stepper motors, grab the motor shaft right now and turn it back and forth. Just a little bit. Just does it have torque?
No.
It's non-zero, right? It takes some torque to drive it, but in general, the motor has no holding torque because you're not applying current to it. So it has, now take the leads of the motor, first make sure they're all separated, and turn the shaft a little bit. Okay. Now connect some of them. If you have the ability to, connect them a little bit together so that a lot of the leads are touching. And what you're doing there is you're actually doing, this is the wiring. If this coil came out to that terminal and this one came out to that terminal, you're actually, if you draw a wire and short that together, you've created, anytime you spin the motor a little bit, you create a little bit of current flow. And you're actually going to feel the motor kind of lock up a little bit when you attach the wires, because you're creating, does that happen? Did you feel that at all?
Yeah.
Right? Okay, so you don't want to do that. It's not a good thing to happen, but I've actually used where I've shorted out the motor cables to each other with some relays to use it as a motor brake. But very seldom you'll ever do that. Answer two, nothing. If you power up that motor, would nothing happen? The only time that would happen is if you're sending it no current, because there's two things that you're watching for in a motor now. One is rotational, is it rotating? But the other is, did it create torque? And if, for instance, let's say it was aligned, that these were aligned right here. This north-south, that's where the rotor and stator were, is along that line, and it was already there when you powered up that winding, it would not move at all. However, if you'd been spinning the motor and it was slightly in a different place and you turned on that winding, it might jump a little bit. But the key is, if current is flowing through this coil, you're creating torque. And so the only way to find out if the motor's creating torque is to grab the shaft and twist it. Okay, so it's an important debug tool is to feel the motor shaft and what it's doing. Okay, three, it heats up. Yes, it would heat up. How much would a motor heat up? What would the big thing depend on?
Current.
Amps.
Right, current. And how are you setting the current in this? How are you setting the current in that winding? What are you doing? What's the key thing that we do in motor control to set the current in a winding?
Use PWM.
PWM, right, pulse width modulation. In other words, you don't just leave this transistor and this transistor on at fully on. You never do that. Unless it's 100% duty cycle, unless you're really maxing out the capability of your device, you wouldn't do that. So you would back off to 70%, 50%, 30%, 10%. It would depend on how much current you're allowed to put through the motor. And some of you are checking your motor data sheets to try and figure out how much current can you put through the motor. But the bottom line is, as soon as you start putting current through it, it's going to start heating up. If it heats up really quick, you're putting too much through it and you need to back off your pulse width modulation. Does it have to be exact? Nope. If you get it a little bit low, it doesn't heat up as fast and it doesn't create as much torque. If it heats up too much, again, heating really depends on how much heat sink you have available as well. So there's not a perfect number. Even if the motor says, oh, you're supposed to run this motor with 1.8 amps. That's the maximum you can put through it. Create 1.8 amps of current. Okay, so 1.8 amps. It still depends on if you've heat sinked it or not. It's a little motor heater. If you've got it really well heat sinked and you have fans, you could probably easily put the 1.8 amps or more. If it's just sitting on your desktop and you put 1.8 amps, it might burn right up. So conditions are important for how much heat you can put through something. So yes, it's probably going to heat up. But the main thing you would see is probably that it jumps when you turn on current. It's more likely that the rotor isn't lined up than it is lined up by a factor of 3 to 1, right? There's 4 total positions. One of them wouldn't jump at all and the other 3 would jump to it. And so it's more likely that it's going to jump to a position and then hold with torque. It's not going to spin. That stepper motors don't just spin. In order to make a motor spin, what has to happen? You have to sequence the current onto these different coils at the right time in the right sequence to make it spin. You're in charge of that. What device is doing that? What devices got the level of controls to be able to sequence these transistors?
Your microcontroller.
Your microcontroller, right. Now, you wouldn't want to have to write those libraries yourself, so hopefully you've picked something that has pre-done libraries that you can just download and it sequences those, okay? So that NAND gate, back to that NAND gate that they put right, let's see, where did they put that? What happened here?
It's right below the AND gate.
Yeah, the NAND gates are on the bottom.
Yeah, okay, AND gate, NAND gate. The reason that one of them has an AND gate, one of them has a NAND gate, because you generally on the same side, you want those transistors never being on at the same time. That is, you either want this one on or that one on, but you never want them on at the same time. So they've given you a NAND gate, which inverts the logic. But the NAND gate has 2 inputs to it. One is from your state table to tell it to turn on. What do you think you should put on the other one? What's it hooked to?
It's a pulse width modulation signal, isn't it?
Exactly. What would happen if on one signal, let's just say that on the input 1, which is coming in here, this is 1, and this is enable A or something like that. If input 1, if you made it go true, you would think that's going to turn on, but you'd never want that transistor just to turn on, because that puts full current to the winding. You want to AND that with PWM. So you want to AND it so that when it's on, it's doing this. And you are setting the duty cycle here based on how much current you want. When you run both of these through an AND gate, guess what you get? You get pulse width modulation signal. You set that once for your motor. That you set it one time depending on how much current you can send to the motor before it burns up. Right? That makes sense? So you set the pulse width modulation duty cycle in your program. It's a number. Well, let's set it at 30%. That's essentially setting the current for the motor, but then you want to only be on that pin when it's time to activate that part of the sequence. So the AND gate is perfect for this, and then down here is the NAND gate, which is the opposite, and it makes it really easy to control the motor. You have 4 pins that are your states, and then an A and B that are your pulse width modulation signals. Should be pretty easy. Now, whether or not your microcontroller has that set up for you already, you may have to write a little bit of code for the pulse width modulation part, I believe. Okay. So you could actually probably figure out pretty quickly what that pulse width modulation frequency should be. For instance, let's say that you have a 100%, start out at 100% duty cycle. Let's start there. You're applying 30 volts roughly to a 2 ohm resistor. You measure the resistance of your winding of the motor. You get out a voltmeter, measure resistance of the motor. Maybe you look it up, but you measure it and it's like, oh, it's 2 ohms. Well, 30 volts applied to 2 ohms is how much current? 15 amps, V equals IR. Then you go look up your motor and it's like, oh, this motor, if I put more than 2 amps through it, it's going to burn up. Oh, okay. So therefore now you have a linearity thing to do, which is 15 amps is 100% duty cycle. X is 2 amps. Right? So 100 divided by 7.5. Oh, there it is. My pulse width modulation frequency should be 22%. Does that make sense? Yes. So that's how you might pick your initial pulse width modulation frequency. You start out with 100% duty cycle gives, is V equals IR. That's no good. We don't want that because that's good. 15 amps is going to burn the motor right up. So you back off of it and figure out what should that initially be. Okay, and that's how you set your initial duty cycle. But generally, they're assuming that you don't have current on both phases at the same time. So when they say 0.9 amps, that's either on phase A or on phase B, but not phase A and phase B, because that would cause way too much motor heating. As you'll see later on when we start to run microstepping, it's actually way more complicated. It's right now we're doing either A or B, and it's either going positive through that coil or negative through the coil, depending on which way you've got, right back to this diagram that we have right now. Sometimes the current's going to be going that way when you have this one and this one on, but sometimes it's going to be going that way. That's the reason you have an H bridge, is so that you have the ability to reverse the current in the winding. So when this one is on and this one is on, then it's going that way. And when this one is on and this one is on, it's going that way. And they're generally assuming you don't have both on at the same time, but you could, and then it would overheat. I mean, basically the stepper motor never turns, it jumps. It just jumps from one step to the next step. And as you make that fast enough, it starts to look like it's turning. But it's always really just jumping from step to step to step to step. And in fact, it's doing this. If we looked at this on a graph and you watched it, let's see if I can do this. Let's put time here and we'll put position on this axis. I think this is going to be right. If you watched it, the stepper motor, you're going to actually be commanding it to do this. Each time you move to a step, every time you move it to this step, it should have increased its position. And in reality, what this really looks like, this is what would be ideal, but in reality, it kind of looks like this. Because it's an undamped spring. Think about what's pulling it around is a magnetic field pulling around a very free to rotate rotor that's on two bearings. And the only thing that as it goes and it bypasses, the only thing pulling it back is the magnetic field. And so you've got a naturally undamped spring that you're pulling around a rotor. So you want to think of it as going step, like these locked steps, when in fact it's more of a boing, 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 boing. And the only thing actually even damping it as this amplitude of the oscillation drops on each step, the only thing actually damping it is either the load that's attached to it, which you don't really have one, it's unloaded, or the friction in the bearings. There's very little to damp it. So it's not a very good system unloaded, but the good thing is that most people don't buy motors to run them unloaded. The whole idea is you're attaching something like a concrete pump to it. So it's loaded, and that concrete pump adds a lot of damping. Anytime you add friction and load, you're generally adding damping. And so in the real world, then this overshoot and undershoot of the oscillation goes away. Okay, so it's a bad little device unloaded. It's highly oscillatory and it causes problems, as you'll see when we get to actually start them turning. Okay, what else?
So if it's moving step by step, how do we achieve the trapezoidal graph that you were showing us earlier?
Yeah. Okay, you have to tell it what you want it to do. So if you want it to move step by step by step, remember back in the controller, you have outputs that control the windings. And it's up to you and the control end of it to make those windings in the sequence that it expects. First phase A, that way. Then phase B, that way. Then phase A, that way. Then phase B, the other way. And you have the H bridge to do it, to reverse the current. So you have those 4 outputs out of your microcontroller that have to run through essentially a little state table. And it's up to you right now to make it do that. This is the cheap way to do stepper motors. And it's kind of important that you as mechatronic engineers know the cheap way, that really, so that when you go to buy a drive that already does all this stuff for you, that you understand kind of what you're buying and why it's worth the money to just buy your way out of this stupid problem. So the answer is, how do you make it turn? You have to turn on the right winding at the right time, at the right frequency to get it to turn. So let's say that you run through this state table. You know, you have A and then B and then A naught and B naught, and then you start out at A again, B. So you're running through this. Let's say that you want in each of these between this, it moves. Oops, what happened? There we go. It moves 1.8 degrees. That's how far the jump is between, that's the natural, when you actually move this is 1.8 degrees. 3.6, what is that? Yeah. So in order to make it go 360 degrees, you have to run through this state table how many times?
200 times.
200.
That's the total number of states. How many? And it's a 4-state table. So how many times do you have to run through the state table to make it turn 1 revolution?
800.
No, the other way. 50.
200.
50 times. 50. See.
50.
Yeah. See. So there's one. Then there's another. So this is 1, 2. This is 1 times through, twice through it, 3 times through it. You do that 50 times, you've hit 200 individual steps. The motor went around 1 revolution. So 1 rev. So you can start to then think of, okay, well, what frequency should you run through these steps. You should run through it. Well, if you want to go 2 revs per second, right? 2 revs per second. And it takes 200, let's see, 200 steps per rev. You better be at 400 steps per second. There's your frequency that you need to run through the state table. Now, the trouble is that if you just give it a fixed frequency, I'm gonna go to the next page here. If you just give it a fixed frequency, and we looked at time and velocity, and you gave it that fixed frequency, it would do this, right? That would be 2 revs per second. And it would just go that speed. But the trouble is, if you ask it to go from 0 and you ask it to just start at 2 revs per second and go, and then you turn off your oscillator or your step sequence advancer, and you just said stop advancing the sequence, it would do that. The problem with that is F equal ma, and you just broke the laws of physics, right? You can't have a mass at a instantaneous velocity. So therefore, what you really want to do is you really want to create this. Okay, the area under this area here, maybe the area, that may be the distance that you want to go. The trouble is you need to figure out how to make it do it and have a deceleration and acceleration. So what that means is as you're going to have a period, some part of your move time that is going to be constant frequency through the state table. The hard part is over here and over here. This part, you have to start at 0 frequency, advancing from state to state to state, and end up at full frequency, keeping track of the total number of steps. And this is where the math starts to get hard for you to write yourself, because these are, now you're doing kinematic equations, you've got an acceleration rate, so therefore you've got a change in frequency, and yet you got to keep track of the number of steps that happened during that time. And so some part of this move, the steps are increasing, some is really easy to cut. This part here, this part here of the move, that's easy to calculate how the distance that went by on that. This is pretty easy to calculate too, the distance that went by on that, assuming that you knew the rate of change of that. And this is pretty easy. This is all just areas, but you can see how to add the acceleration and deceleration part of this, that's why you like somebody's pre-written libraries, where you can just type in, oh, what's the acceleration rate that you want to use? And they plug that into some kinematic formulas, and they say, how much distance do you want the overall move to be? And it figures out how much is in each of those parts. The math is done. That's the part, and I don't really want you having to write that math. I really want you to find libraries that already did the acceleration for you. But you do have to deal with accelerations in your advancement through your state table.
So I found like a Arduino library called Excel Stepper. Would something like that be fine?
Yep. Yep. That's generally what I remember it being called, yes. And it has some limitations to it, but that's what you're after. Is you can't just say to a mass, hello, please be at speed instantaneously. It just doesn't do that. This is complicated, right? Because all this stuff is kind of new but hopefully that's why you kind of work yourself through it, and you got to think through until you finally conclude, okay, I got to find a library that does these 4 inputs and cycles them, and I got to accelerate it, and I need pulse width modulation. You got to do 2 things to make this motor turn. You got to cycle through the phases, and you have to control the current. So remember, the L298 is a little board with the 298 chip on it. And so it added a heatsink. Now, if you look at the ST microelectronics data sheet, it doesn't show a heatsink. It just shows the little chip with all the little legs coming off of it, right? Except for the people, whoever it was that built your board, they put a heatsink on it. All right, that heatsink is going to get hot at some point. So what's the maximum voltage that that device can handle? Maximum 46 volts. Okay, how much current? 4 amps. Now, how's that divided up? 2 amps per phase. We'll call it per phase, which is fine because that's what you want. So basically, 2 amps per phase is the maximum that you can put through this. You probably can't put 4 amps through a single phase, but what they're saying is you could have 2 amps and you could have 2 phases on at the same time if you wanted to at 2 amps, and it could handle the heat. In general, you're not going to do that. You're going to have 2 amps either on this one or on that one, or flip the direction around and have it back on this one or on that one. Those are your 4 states. The time that you would actually have it on both would be something called half stepping, where you're actually trying to get higher resolution, and all of a sudden your state table became more complicated because now it has not just 4 states, it would have some states in there where you cut back pulse width modulation duty cycle to lower the current. So for instance, if you had, let me just draw this real quick here. Let's say that you had phase A, and that's this coil. And then here's phase B, and that's this coil. And there's H bridges around each of those. Generally, I'm saying either A or B, or A the other way or B the other way. You can go either direction, but in half stepping, what happens is if you turned on phase A, and so you have current running through that, and you had phase B at the same time, the L298 can run up to 2 amps through both of those and not overheat. However, it doesn't mean that the motor could handle that. If it's a 2 amp per phase motor and you had current through both of those, your motor would probably overheat. So what do you do if you want to have both of them on? If you have, first of all, back to, let me go back to this diagram right here. This diagram right here. If, for instance, in this diagram, you had 2 phases on at the same time, let's say here's your magnet. This is kind of getting, let's say this is your magnet, this south-north magnet, and I told you to align it with this north-south coil. Okay. But let's say that you had this coil, which is B, and this coil, which is A, and you turn both of these on at the same time. Where would the rotor go?
Between them.
It would go between them. So it makes an intermediate step. However, if you turn that one on at 2 amps and that one on at 2 amps, what happens? The H bridge can handle it, but the motor can't get rid of the heat. So what do? If you want this intermediate step, what do you do if you want this intermediate step right here? It's not over here, it's here. It's intermediate steps called half stepping. You have to, when it's in that one state of the state table where both of them are on, because you fired, instead of firing OR inputs, 1 or 2 or 3 or 4 out of your Arduino, you said, okay, we're going to do 1, then we're going to do 1 and 3, then we're going to do 2, then we're going to do 2 and 4, then we're going to do 1, 1 and 3. You added this extra step where you turn on 2 windings at the same time because you have control over that with your logic. You would, in that one state where both of them were on, you have to cut back your PWM such that the magnetic strength of this coil and this coil are less, otherwise you'll burn their motor up, right? Or cut back the whole thing. But and this is the hard part about for you guys, where you're setting the PWM and you're running the state table. I'm really asking you to, you know, really be in control of this thing. But those are the two things: position and current control are up to you. One other question that a bunch of you had was, I can't find the data sheet for this motor. What do I do? Well, this motor is a really simple thing. It is a coil. Remember, it's three things. It's a electromagnet, it's a heater, and it's an inductor. It has those three properties. You want the electromagnet, but you got to put up with these other two that are bad, generally. So it's a coil wire. A coil wire has two ends to it. How do you find the two ends of the coil? If you don't have a data sheet to look it up, test the resistance. And when you test the resistance, you're going to test for which two wires have continuity, and then you're also going to learn what's the actual resistance. That's going to help you to set the current. How many ohms is it? Oh, it's 1 ohm. Whoa, that's a low resistance winding. Or maybe it might be 5 ohms. Like, wow, that's got a lot of coils in there. That's a lot of turns of coil. What does that tell you? It's high inductance, and it's going to be a strong electromagnet, right? So in general, that's, by the way, that's the range we're at. In 0.5 ohm to 3 or 4 ohms is about the range of resistance that you're going to encounter in motor windings. Basically, you can run a motor by figuring out what are the, where are the windings, and just keeping track of it. You don't really need, and then how much current do you give it right at first? Well, start on the low end. Start with, and let it heat up. Don't start with 30% duty cycle on your pulse width modulation. Start with 5% duty cycle. And if it stays cold, bump it up to 7. So start low so you don't burn it up, and then raise it up as you need more torque to do what you do, and keep putting your hand on the motor. And if it starts getting hot, turn it off real quick and lower the pulse width modulation duty cycle back down. You were too high. That's all. That's really all you got to do to drive a motor.